Funny when you think about how these huge language models are popping up everywhere, right? They're being trained with crazy efficiency and they have billions or even trillions of parameters.
Yeah, it's wild.
But for regular folks like us, all that size doesn't always translate to speed when we want to actually use them.
Right.
Take Mixture of Experts or MOE, for example. They're designed so that only the parts needed for a specific task are activated during training, which makes them incredibly efficient in terms of training costs.
Yeah, exactly. It's all about that selective activation. They can handle way more parameters than a typical dense model without the training costs skyrocketing.
Totally. But here's where it gets interesting, and this is straight from the Ultra-Sparse memory network paper you sent me.
Okay.
Even if a MOE model has the same computational requirements as a smaller, dense model, and sometimes even 10 times more parameters, it can be 2 to 6 times slower when it's actually doing things like generating text or answering questions.
Uh-huh.
That kind of lag just won't cut it for most real-world uses.
Absolutely. Figure 1C in the paper actually shows this really well. It all comes down to memory access.
Okay.
Even with only specific experts activated, the systems still have to fetch their parameters from memory, and all that back and forth really slows things down during inference, which is when the model is actually being used.
Right. And that brings us to something you flagged for me that seems really promising, UltraMem.
Yes.
From what I see in your notes in the paper, this new architecture looks like it's specifically designed to break through that speed barrier. So what's the main idea behind UltraMem?
So the core promise of UltraMem, as both your notes and the paper highlight, is to dramatically cut down that inference latency we've been talking about. But doesn't stop there.
Okay.
The goal is to keep or even improve the performance we're seeing in these large models, all while ensuring it can scale effectively as we build even bigger models in the future. And what's really cool is that UltraMem builds upon and significantly improves the concepts introduced in product key memory, or PKM.
Interesting. So let's break down that connection a bit.
Sure.
We've talked about the inference challenges with MOE, and you mentioned product key memory, or PKM. For those who might not be familiar, what exactly is PKM and how did it pave the way for UltraMem?
So think of PKM as another way to create massive memory layers within a neural network.
Okay.
Instead of using dense connections like in standard models or selectively activating large chunks of the network like in MOE, PKM uses this smart indexing system.
Okay.
It employs a 2D logical address, kind of like coordinates on a map, to pinpoint specific memory values.
Okay.
This allows for a much faster way to calculate the relevance scores for a huge number of potential memory locations by splitting the scoring into separate row and column calculations. Imagine a giant lookup table where you can quickly find what you need just by knowing its approximate location.
I get it. So PKM is also aiming for efficiency when dealing with these massive amounts of memory. But it sounds like the paper suggests it wasn't the perfect solution.
Yeah, that's right. While PKM provides a more consistent memory access pattern during inference and can work with fewer unique memory embeddings, the ultra-sparse memory network paper points out that its performance hasn't quite matched up to Mo.
Okay.
And on top of that, the original PKM architecture just isn't built for training the really massive billion parameter models that are becoming more and more common these days.
I see. So UltraMem comes in as a significant upgrade to PKM. What are the really groundbreaking innovations that allow it to overcome these limitations and, most importantly for us, tackle that inference speed problem head on?
Well, UltraMem has several very clever advancements. First off, there's something called Tucker Decomposed Query Key Retrieval, or TDQKR for short.
TDQKR. That sounds pretty technical. Can you break down what TDQKR does within UltraMem?
Sure. At its core, TDQKR is how UltraMem finds and retrieves the most relevant information from its memory. It replaces the product quantization used in PKM with a technique called Tucker decomposition.
Okay.
Now, think of Tucker decomposition as a way to take a very large and complex set of relationships, in this case, the relationships between the input, which we call the query, and the info stored in memory, which are the keys, and break it down into a more manageable core component and a set of simpler related parts. Okay. By doing this, UltraMem aims for a much more precise and nuanced retrieval of information compared to PKM's more basic product quantization.
So instead of PKM's approach using row and column scores, TDQKR introduces this Tucker decomposition step in between.
Exactly.
How does that actually lead to retrieving the right information more accurately?
Well, the Tucker decomposition allows the model to capture much more complex interactions between those row and column scores when it's trying to estimate what the paper refers to as grid scores.
Grid scores. Got it.
As Figure 4 in the paper shows conceptually, it uses a Tucker core to model these interactions. Essentially, it's a more sophisticated way of combining the initial pieces of information to really pinpoint the most relevant memory locations. It's like going from guessing the general area to knowing the exact address.
That makes sense. You also mentioned a rank approximation in this process. Is that a way to keep the computational cost manageable?
Exactly. Doing a full Tucker decomposition for every single retrieval would be computationally very expensive.
Right.
So they use a rank-R matrix multiplication, which is shown in equation 5, to estimate these grid scores efficiently.
Okay.
Interestingly, their experiments showed that a relatively low rank of just 2, RE2, worked surprisingly well.
Wow.
To further optimize the top M selection, which has identified the top M most relevant memory slots, they approximate the Tucker core itself using an even simpler rank 1 decomposition, as detailed in equation 6.
Okay.
This two-stage approximation allows the accurate retrieval without a huge computational overhead.
So they're being smart about using approximations to balance accuracy with speed. Now, I also remember something about an auxiliary loss being used in training this TDQKR component. What's that all about?
Ah, good catch. That's equation 12. During training, they use this auxiliary loss function to keep the approximation error in check.
Got it.
It basically penalizes the less significant components, the non-maximum eigenvalues, of the Tucker core, encouraging it to stay close to that efficient rank 1 approximation we discussed, but without losing the benefits of the initial, more complex Tucker decomposition.
Okay.
This helps ensure that the speed optimizations don't come at the cost of significantly reduced accuracy.
Got it. So we have more precise information retrieval that's optimized for speed through these clever approximations and training techniques. What's the next big innovation UltraMem brings to the table? I think you mentioned something called implicit value expansion, or IVE.
Yes, IVE is a really elegant way that UltraMem tackles both the cost of accessing a massive memory and the ability to scale that memory to truly enormous sizes.
Okay.
You see, the fundamental problem with having a truly gigantic memory table in a neural network is, well, its size. It takes up a lot of memory resources, and accessing specific parts of it can become a bottleneck. IVE creates the illusion of a much larger memory, what they call a virtual memory, without needing to physically store all of it at all times.
Virtual memory for AI models. That's pretty fascinating. How do they pull that off?
They do this by reparameterizing a smaller physical memory table using a set of linear transformation matrices or projectors, as described in equation 13 and shown in figure 5. Think of these projectors as different lenses through which you can view the base physical memory.
Interesting.
For a given virtual expansion rate, denoted as E, they can effectively make the memory appear E times larger than its physical size. Their experiments suggest that a virtual expansion rate of 4E4 strikes a good balance.
So the model acts as if it has a much larger memory capacity than it physically does. But how does it actually access these virtual blocks of memory?
The trick is that this reparameterization isn't computed for the entire virtual memory all the time. It's done only when needed.
Makes sense.
After calculating a weighted sum of the retrieved keys, the model figures out the index of the virtual memory block it needs and then computes the reparameterization using equation 15.
Okay.
This on-demand computation significantly reduces the overall computational cost and, most importantly, the amount of GPU memory accessed at any given time. It's like having a compressed version of a massive library that could be quickly uncompressed to access specific sections as needed.
That's incredibly clever. So TDQKR improves how information is found, and IVE makes having a massive memory practical. Is there a third core innovation that completes this picture?
Yes, the last major innovation in UltraMen's core architecture is called multi-core scoring, or MCS.
Multi-core scoring, does that mean it's using multiple processing units in the hardware?
Not in the physical hardware sense, but rather within the model's architecture itself. Instead of using a single Tucker core to generate one set of relevance scores for the memory values, MCS uses multiple component cores, denoted as CII in equation 16. Okay, each of these component cores creates its own individual score map, Tucker, focusing on different parts or aspects of the value table.
I see.
Their experiments suggest that using two component cores, H equals 2, works well.
So it's like having multiple independent judges evaluating how relevant a piece of information in memory is to the current input.
Exactly. And by having these multiple independent scoring mechanisms, the model can capture more nuanced and diverse relationships between the input query and the different aspects of the information stored in memory.
Okay.
While the final selection of the top M most relevant items is still based on an aggregated score, which is the sum of the individual score maps, the individual scores are then applied to a value table that's been split vertically into corresponding parts, as shown in equation 17.
Right.
This allows for a richer interaction between the relevant scores and the actual information being retrieved, ultimately leading to better overall performance.
So to recap the core architectural innovations of UltraMem, TDQKR for more precise and efficient retrieval, IVE for enabling large virtual memories with lower access costs, and MCS for a more nuanced and effective way of scoring memory content. It definitely sounds like a major step forward from standard PKM.
It is.
Now, I also noticed in your notes a mention of a bag of tricks, a set of structural improvements over PKM that further contribute to UltraMem's
Oh
advancements.
yeah, those are important too.
What are some of those key tweaks?
So beyond those fundamental architectural changes, the researchers also implemented a series of important structural refinements to the baseline PKM architecture. These are detailed in Section 3.2 of the Ultra-Sparse Memory Network paper.
Okay.
These might seem like smaller changes, but together they make a big difference. UltraMem's improved performance and stability.
Got it. Tell me about some of these tricks of the trade.
Okay, so first they found that removing the softmax activation function from the score aggregation actually improved results, which aligns with other recent research on similar architectures.
Interesting.
Second, they applied layer normalization to both the query and the keys before the attention mechanism, a common technique to improve training stability in deep neural networks.
Right.
Third, instead of using a fixed learning rate for updating the values in memory, they found that gradually decreasing this learning rate during training led to better performance.
Okay, what else did they do?
They also improved the way the query is processed by adding a causal, depth-wise convolutional layer before the linear layer that generates the query vector.
Got it.
Fifth, they borrowed a technique similar to group query attention, where the query is shared across the two sets of keys.
Uh-huh.
This reduces the computational cost of key processing without significantly impacting performance.
Clever.
Sixth, they made an interesting adjustment to the dimensions of the value embeddings.
Okay.
They have the dimension of each value vector, but double the total number of values stored, and consequently double the number of top-M selections. This was done to increase the diversity of the information retrieved.
Makes sense.
Finally, and this is especially important for training very large models, they broke down the large memory layer into multiple smaller layers and distributed them across different transformer layers using skip connections.
Okay.
This skip layer structure helps with balancing the computational load across multiple GPUs and allows for more efficient parallel processing during training.
Wow, that's a whole lot of optimizations. It seems like they've really fine-tuned various aspects of the architecture to maximize efficiency and
They
performance.
really have.
So what are the actual tangible benefits of all these innovations and structural changes? How does UltraMem actually perform compared to something like MOE in terms of jumbers?
Well, the quantitative analysis in the paper really highlights UltraMem's advantages, especially when you look at the memory access cost during inference. As we talked about earlier, UltraMem has a significantly lower memory access cost compared to MOE.
Right?
They even have a theoretical analysis showing that UltraMem's memory access scales much better with increasing batch size than MOE's.
And in practical experiments, what kind of speed improvements are we talking about when using UltraMem?
The experimental results are quite impressive. They found that UltraMem can be up to 6 times faster than MOE for inference, while using the same number of parameters and computational resources at common inference batch sizes. What's even more remarkable is that UltraMem's inference speed is almost the same as a dense model with comparable computational resources. For anyone looking to use these advanced models, that kind of speed boost is a game changer.
6 times faster with the same resources? That's incredible. It could really open up new possibilities for using these powerful models. What happens when we start thinking about scaling to even larger models? Does UltraMem keep its advantages as the models grow?
Yes, the scaling experiments in the paper are quite impressive. They show that UltraMem consistently outperforms both PKM and MOE as the model size increases, even when all three architectures have the same number of parameters and computational budget. They even found that a 1.6 billion parameter UltraMem model could perform as well as a 6.5 billion parameter dense model.
Wow.
That's a remarkable increase in effective model size for the same computational investment.
That kind of scaling efficiency is really significant. But with all this focus on sparsity, are there any inherent trade-offs? For example, how does the number of activated memory slots impact performance?
That's a great question. The researchers looked into the relationship between sparsity, which is controlled by the top-M hyperparameter, meaning the number of memory slots retrieved, and the total number of values stored, and how it affects performance. Okay, as figure 6b in the paper shows, reducing sparsity, which means activating more memory slots, generally leads to better performance. However, this also means increased memory access during inference.
Right, so there's a balance to be struck.
Exactly. The optimal level of sparsity depends on the specific application and the available hardware. What's interesting is that, as figure 6c highlights, UltraMem's inference time stays pretty stable even when the total number of sparse parameters increases, as long as the number of actually activated parameters top M stays the same.
Okay.
This is a key advantage over MOE, where inference time tends to increase more noticeably in similar situations.
So UltraMem seems to handle increases in the total number of sparse parameters much better when it comes to inference speed.
Exactly.
The paper also includes detailed ablation studies. What were the main takeaways from those in terms of validating the different innovations?
The ablation study, detailed in Table 2 and Table 3 of the paper, provides strong evidence that the various components of UltraMem are effective.
Okay.
They systematically removed or changed different parts of the architecture, like the structural improvements, TDQKR, IVE, MCS, and the initialization techniques, and carefully measured how it affected the model's performance.
Got it.
These studies highlighted 6 specific changes that led to significant performance gains:
Okay.
doubling the number of values stored, distributing the large memory layer across multiple transformer layers, incorporating TDQKR and MCS, implementing IVE, and using the gradually decaying learning rate for the values. These findings strongly support the idea that each of these innovations contributes significantly to UltraMem's overall performance and efficiency advantages.
It definitely sounds like UltraMem offers a compelling solution for addressing some of the major challenges in scaling large language models, especially when it comes to inference efficiency.
I agree.
But what about the practical aspects of actually training such massive models with this ultra-sparse memory architecture? Are there any specific techniques required?
That's a good point. The researchers did address this.
Okay.
They used Megatron's well-established 3D parallelism framework, which includes pipeline, data, and tensor parallelism, and adapted it with specific modifications to enable efficient training of UltraMem models with billions of parameters. This is all explained in Appendix C of the paper.
So they were able to effectively distribute the training workload across many GPUs.
Exactly. They describe how they shard the memory table itself, both in terms of the number of memory slots and the dimensions of the value vectors across the available GPUs.
Got it.
This sharding strategy is discussed in more detail in Appendix D. They also implemented a special fused lookup reduce operated and an asynchronous execution strategy to further optimize the training process and achieve better performance when training at this massive scale. These optimizations help streamline the computations and minimize memory bottlenecks during training.
It really seems like UltraMem has made significant progress in addressing the critical bottlenecks associated with large language models, especially when it comes to inference speed.
Absolutely.
To sum it all up for our listeners, what are the most important things to take away from our deep dive into UltraMem?
The key takeaways are that UltraMem presents a novel architectural design, notably featuring its Tucker decomposed query key retrieval, implicit value expansion, and multi-core scoring mechanisms, along with some crucial structural improvements.
Okay.
These innovations all work together to significantly reduce inference latency compared to mixture of experts models, often reaching speeds comparable to dense models with similar computational costs. Plus, UltraMem scales incredibly well, consistently outperforming Mo as model size increases.
So UltraMem offers a promising way to use highly effective language models in environments with limited computational resources and to develop even larger, more capable models without the incredibly high inference costs associated with other sparse architectures. It feels like a big step forward for the field.
I completely agree. It solves a fundamental challenge and unlocks exciting new possibilities.
Thinking about these efficiency gains with UltraMem, it really gets you thinking, doesn't it?
Yeah, it does.
What entirely new applications for large language models might become possible, especially in areas like edge computing or real-time interactive systems where even a tiny bit of lag can be a major issue? And what does the emergence of these ultra-sparse memory networks mean for the future of AI? These are things I encourage everyone to consider.
It's definitely worth pondering. The potential is huge. And UltraMem seems to be a key that could unlock many applications that were out of reach before.
It really does. Well, this has been a fascinating deep dive. Thanks for sharing your insights.
My pleasure. It was great discussing this with you.
And to all our listeners, thank you for joining us on this deep dive into UltraMem. We'll see you next time.
See you then.